2012, 6 billion miles from the nearest human being. A spacecraft older than most of the people who will ever watch this woke up long enough to send a number back to Earth. It was running on less electrical power than a refrigerator light bulb. Its instruments were designed in the 1970s, in an era when the Apollo program was still a recent memory and the personal computer didn't yet exist. And what it sent home in the last weeks of 2018 wasn't really a triumph, even though it was reported as one. It was a data point that has been sitting quietly in the peer-reviewed record ever since, largely unnoticed outside a fairly narrow circle of specialists. The plasma density around the spacecraft jumped sharply. Cosmic ray counts spiked. And the boundary between our solar system and everything outside it turned out to be sharper, thinner, and considerably less forgiving than most of the models built to predict it had assumed. The press release called this a historic crossing. The data, read carefully, described something closer to an exposure. Before we go any further, I want to ask you to do something. Look up, wherever you're watching this, from whatever city, whatever room, whatever quiet corner of the world you happen to be in tonight. And remember something we tend to forget entirely. Everything above you right now, the moon, the visible planets, the stars, the whole familiar arrangement of light and dark we call the night sky, is happening inside a bubble, not a metaphor, a physical, measurable, three-dimensional shell of charged particles and magnetic field, roughly teardrop-shaped, blown outward by our own sun, standing between the solar system and the raw radiation environment of the wider galaxy. And in 2018, after 4 decades of near-total silence, a small, aging spacecraft called Voyager 2 finally reached the edge of that bubble and told us, for the first time with real, direct measurement, exactly how thin the wall actually is. That's not quite the story most people were told at the time. And that gap between the version that made the evening news and the version sitting in the technical papers is worth taking seriously, not with alarm, and not with any suggestion that anyone deliberately hid anything, just with the actual numbers, read carefully, and followed all the way to where they actually lead. What Voyager 2 actually measured. The public version of this story is simple, and as far as it goes, entirely true. In November 2018, Voyager 2 became only the second human-made object in history, after its twin Voyager 1 6 years earlier, to cross the heliopause and enter interstellar space. Ed Stone, the mission's longtime chief scientist, appeared at press conferences looking, by every account, genuinely delighted. Reporters used the word historic in headline after headline, and it was historic. A genuinely remarkable engineering and scientific achievement, a spacecraft launched during the Ford administration reaching a boundary nobody at the time of its launch had any real way of picturing in detail. What received far less attention, outside the pages of the specialist journals that actually published the results, was the specific character of what the spacecraft's instruments recorded on the way out. The formal results, published in a set of companion papers in Nature Astronomy in 2019, did not describe a gentle, gradual fade from one environment into another. They described a boundary crossed in a matter of hours rather than the weeks or months some earlier models had allowed for. They described a jump in plasma density sharp enough to look, in the data, almost like a physical wall. And they described a cosmic ray environment on the interstellar side that came in harsher and more energetic, in several respects, than 6 decades of accumulated theoretical modeling had anticipated. None of that made it into most of the headlines, and it's worth being fair about why, rather than assuming anything sinister. A number describing the steepness of a plasma density gradient is not, on its own, a compelling television moment. Historic crossing is. This is less a story about concealment and more a story about the ordinary mechanics of science communication. What gets emphasized in a press conference is not always what keeps the scientists themselves up at night afterward, And the distance between those two things is where a great deal of the most important context in science quietly goes missing from public understanding. So it's worth pausing here and actually explaining what the heliosphere is in some real detail, because without that grounding, nothing that follows in this documentary will land the way it should. Our sun is not a passive light bulb sitting quietly at the center of the solar system. It is an active, outward-pushing engine, constantly blowing a stream of charged particles, mostly protons and electrons, outward in every direction, at speed. Is typically somewhere between 400 and 800 kilometers per second, depending on which region of the sun's surface they originated from. This is the solar wind, and it inflates an enormous bubble of ionized gas around the entire solar system, pushing back continuously against the thin but real pressure of the interstellar medium beyond it. That bubble, roughly teardrop-shaped because of the solar system's motion through the surrounding galaxy, is the heliosphere. It extends far beyond the orbit of Pluto, far beyond the Kuiper belt, out to a boundary called the heliopause, the point where the outward push of the solar wind finally loses out to the inward pressure of the galaxy itself. Inside that boundary, the inner solar system is meaningfully shielded from the harshest radiation the wider galaxy has to offer. Outside it, that shielding effectively ends. Voyager 2, for the first time, let us measure directly what that transition actually looks like, rather than inferring it indirectly from models built on decades-old, comparatively sparse data. And what it found, in the specific numbers, was not quite what those models had confidently predicted going in. Say, a bubble we live in. It helps to think of the shielding protecting the inner solar system as a nested structure, layer with and layer, each one doing a different part of the job. A picture most people never really encounter outside of specialized astrophysics courses, but one that's worth holding in mind for the rest of this documentary. The outermost layer is the heliopause itself, the boundary Voyager 2 crossed in 28. Just inside that sits the termination shock, the region where the outward flowing solar wind, which travels at supersonic speed for most of its journey through the solar system, abruptly slows to subsonic speed as it begins colliding with the resistance of the interstellar medium pressing in from outside. Inside the termination shock lies the vast interior volume of the heliosphere itself, filled with solar wind plasma and threaded through with the sun's own outward carried magnetic field, encompassing the orbits of all 8 planets and reaching, in some directions, well over 100 times farther from the sun than Earth does. Much closer to home, wrapped around Earth specifically, sits a second and entirely separate shield, the magnetosphere, generated not by the sun, but by the churning motion of Earth's own molten iron core, deflecting the great majority of charged particles that make it past the outer heliospheric shield before they ever reach the top of our atmosphere. And closer still, forming the final layer, sits the atmosphere itself, absorbing and scattering much of what does slip through the first 2 shields. 4 layers, in other words, each one thinner and more localized than the one before it, together doing the quiet, continuous, almost entirely unnoticed work of keeping the harsh radiation environment of the wider galaxy off the surface of this particular planet. Voyager 2 measured the outermost of those 4 layers directly for the first time in human history, and what it found did not match every expectation built into the models. What that outer layer actually protects us from is worth naming plainly, because it's easy to let the phrase cosmic radiation wash past as an abstraction. Galactic cosmic rays are the accumulated high-energy particle output of the wider galaxy, the debris of exploded supernovae, the accelerated particles flung outward by the violent environments surrounding distant neutron stars and black holes, arriving at the edge of our solar system after having traveled, in many cases, for thousands or millions of years across interstellar space, moving at a meaningful fraction of the speed of light. Almost all of it is deflected, scattered, or absorbed by the nested shielding described above, before it ever reaches a human body on Earth's surface. The heliosphere is not a piece of background astronomical trivia. Functionally, it operates as a life support system, and every human being who has ever lived, every hunter-gatherer, every pharaoh, Newton, Einstein, everyone who has ever thought a single thought, has done so entirely within its protection, without exception, and largely without ever knowing the shield was there at all. Which is exactly why what Voyager 2 measured on its way through matters as much as it does. It didn't simply confirm that the wall exists, something already assumed with reasonable confidence. It gave us our first real, direct read on how thin, how sharply defined, and, as the following sections of this documentary will lay out, how variable that wall actually is over time. T-leak. Here is the part of this story that deserves more attention than it has generally received. The cosmic ray subsystems carried aboard both Voyager 1 and Voyager 2 have been tracking the flux of galactic cosmic radiation continuously for decades, and their readings are independently corroborated by a global network of ground-based neutron monitor stations that have been recording cosmic ray activity reaching Earth's surface since the middle of the 20th century. Taken together, this long-running body of measurement shows something worth sitting with. The level of high-energy galactic cosmic radiation reaching the inner solar system has been trending upward in recent decades, and during the most recent solar minimum, neutron monitor stations recorded some of the highest cosmic ray flux levels seen anywhere in the space age. The underlying mechanism connecting these two facts, a weakening heliospheric shield and rising cosmic ray flux at Earth, is straightforward physics rather than speculation. The strength of the heliosphere's outward push, and by extension its effectiveness at deflecting incoming galactic cosmic rays, is directly tied to the intensity of the solar wind, which itself rises and falls with the sun's roughly 11-year activity cycle. During periods of higher solar activity, a stronger solar wind inflates a more robust heliosphere, doing a correspondingly better job of deflecting cosmic radiation before it reaches the inner solar system. During quieter solar periods, that shielding effect measurably weakens, and cosmic ray flux at Earth correspondingly rises, an inverse relationship that has been documented and refined across more than half a century of continuous neutron monitor data, and one considered well-established rather than controversial within the solar and space physics community. What makes the current situation worth flagging is that solar cycle 24, which ran from roughly 2008 to 2019, was one of the weakest solar cycles recorded in more than a century of systematic observation. A genuinely unusual, historically quiet stretch of solar activity. The cosmic ray flux measured at Earth during the associated solar minimum around 2009 to 2010, and again during the following minimum around 2019 to 2020, registered among the highest levels recorded since neutron monitoring began in earnest in the 1950s. This is not a projection or a model output. It is a direct, repeated, independently corroborated measurement, and it carries a concrete implication worth stating plainly. The radiation shielding that protected the Apollo astronauts on their way to the moon in the late 1960s and early 1970s was measurably stronger, on average, than the shielding protecting astronauts aboard the International Space Station today. Every future long-duration astronaut, in other words, is inheriting a somewhat thinner sky than the one their Apollo-era predecessors flew under. Not a catastrophic difference in any single mission, but a real, measured, and so far one-directional trend. It's worth being careful and honest about the limits of this picture, because overstating a real trend is its own kind of distortion. Solar activity is cyclical, and solar cycle 25, currently underway as of this documentary's writing, has come in somewhat stronger than initial forecasts anticipated, which would, if the trend continues, correspond to at least a partial, temporary strengthening of the heliospheric shield over the next several years. Whether the broader multi-decade pattern represents the beginning of an extended period of generally reduced solar activity, something loosely comparable to, though not necessarily identical to, the 17th century Maunder minimum discussed later in this documentary, remains a genuinely open, actively debated question among solar physicists, with published models pointing in more than one direction. What's not seriously in dispute is the underlying physical relationship itself, or the specific, measured fact that recent solar minima have coincided with some of the highest cosmic ray flux levels of the entire space age. The size and permanence of the long-term trend is uncertain. The direction and mechanism behind the recent measurements are not. WY Mars isn't just a longer road trip. This is where the public conversation about deep space exploration tends to quietly break down, and it's worth spending real time on why. When people talk casually about sending astronauts to Mars, the framing is often something close to a longer version of going to the moon. Farther, slower, more expensive, but fundamentally the same category of undertaking, just scaled up. That intuition turns out to be wrong in a specific, physically important way, and the radiation numbers make the reason clear almost immediately. The moment a crewed spacecraft leaves low Earth orbit, it exits Earth's magnetosphere, the innermost of the 4 protective shielding layers described earlier, and the one specifically generated by our own planet, doing most of the day-to-day work of deflecting the charged particles the Sun and the wider galaxy constantly throw at us. Astronauts aboard the International Space Station remain, for practical shielding purposes, largely inside this layer for the duration of their mission. Apollo astronauts left it too, but only for a matter of days at a time. The longest lunar missions kept crews outside the magnetosphere's protection for roughly a week to 12 days total. A Mars-bound crew, by contrast, would spend somewhere in the range of 6 to 9 months in transit each way, depending on trajectory, with total mission time, factoring in transit and a stay on the Martian surface, potentially stretching to somewhere between 18 months and closer to 3 years. That is not a modest increase in exposure time. It's an entirely different order of magnitude, sustained continuously, with no equivalent in the whole of human spaceflight history to date. We're not entirely reliant on modeling to estimate what that exposure would actually look like, because NASA's Curiosity rover carried an instrument specifically built to measure it directly. The Radiation Assessment Detector, or RAD, recorded the radiation environment throughout Curiosity's own roughly 253-day cruise to Mars in 2011 and 2012, and the results published by Zeitlin and colleagues in Science in 2013 were not especially reassuring. The instrument recorded a cruise phase dose equivalent of roughly 1.8 millisieverts per day, which, extrapolated across a comparable round-trip transit alone, setting aside any additional exposure accumulated during time actually spent on the Martian surface, works out to somewhere in the neighborhood of 600 to 700 millisieverts before a single boot ever touches Martian. So, to put that figure into some meaningful context, an astronaut aboard the International Space Station working within the partial protection of Earth's magnetosphere typically accumulates somewhere around 150 millisieverts over the course of a standard 6-month rotation. The Mars transit alone, based on the Curiosity RAD data, would likely deliver somewhere between 4 and roughly 7 times that amount, without the benefit of any planetary magnet like shielding at all, spread continuously across every single day of a months-long cruise. NASA's own historical career radiation exposure limits for astronauts, set, broadly, to keep lifetime excess cancer risk under roughly 3%, and varying by an individual astronaut's age and sex, have generally sat somewhere in the range of 600 to 1,200 millisieverts across an entire career. A single Mars round-trip transit alone on these figures could plausibly consume the greater part, or in some scenarios essentially the entirety, of a typical astronaut's whole career radiation budget in one mission. And that's before accounting for the additional, harder-to-predict risk posed by a major solar particle event, an unusually intense solar flare or eruption arriving at an unlucky moment, which in a worst-case scenario could deliver a dangerous acute dose in a matter of hours rather than months. The deeper point worth taking from these numbers isn't a single precise figure. Legitimate uncertainty exists around exact risk models, individual variation, and the specific shielding configuration any real mission would ultimately fly with. But the underlying category of the problem, going to Mars, is not simply a longer version of going to the Moon. It's a sustained, months-long departure from the protective magnetic shielding the human body, and every human body before it across the whole of our evolutionary history has always had available. And that departure changes what risk actually means for the mission in ways that scaling up an Apollo-era plan doesn't fully capture. The body under bombardment. Given how much time human beings have spent, evolutionarily, safely tucked inside Earth's protective shielding, it's worth asking directly, what actually happens to the human body when that protection is removed for months at a time? The honest answer is that we're still learning in real time, and what we've learned so far is not entirely comfortable. The most detailed data set we currently have on extended time in a partially shielded environment comes from NASA's twin study, published in Science in 2019, which compared astronaut Scott Kelly, following a nearly year-long stay aboard the International Space Station, against his identical twin brother Mark, who remained on Earth for the same period, offering an unusually well-controlled natural experiment given the twins' shared genetics. The study documented measurable changes across a range of biological systems, shifts in gene expression, alterations in immune function, changes in telomere length, and some differences in cognitive test performance following the mission. Some of these changes reversed within months of Scott Kelly's return to Earth. Others, notably including certain gene expression changes and some cognitive test results, persisted for longer, and a small number appeared not to have fully returned to baseline even at the study's later follow-up points. It's worth being precise about what this study does and doesn't show. Scott Kelly spent his entire mission within the partial protection of Earth's magnetosphere aboard the ISS, meaning his radiation exposure, while elevated relative to life on Earth's surface, was nowhere close to what an unshielded deep space transit to Mars would involve. The twin study represents, in that sense, a comparatively mild preview of what extended time outside full planetary protection can do to the human body, not a direct simulation of the Mars radiation environment itself. For a closer approximation of what fuller deep space exposure might involve, researchers have turned to ground-based particle accelerator facilities, most notably NASA Space Radiation Laboratory at Brookhaven National Laboratory, where scientists can generate beams of particles designed to simulate the specific mix and energy profile of galactic cosmic rays and expose laboratory rodents to doses roughly comparable to what a Mars transit crew might accumulate. The results of this line of research, published across numerous peer-reviewed papers over the past decade or more, have documented measurable, sometimes persistent cognitive effects in exposed animals, including impaired performance on spatial memory and decision-making tasks, along with detectable structural changes in neurons, formally described by some researchers in the field as a kind of space fog. It's important to be appropriately cautious extrapolating from rodent studies to human outcomes. The translation from animal models to human neurology is never perfectly direct. Dose comparisons involve real uncertainty, and this remains an active area of ongoing research rather than a settled, fully quantified human risk. But the consistent signal across multiple independent studies is concerning enough that NASA's own human research program treats cognitive and behavioral risk from deep space radiation as a genuine, actively studied category of concern, separate from the more familiar, longer-term cancer risk that radiation exposure has traditionally been associated with in public discussion. And the distinction matters operationally. A cancer risk that might manifest decades after a mission is a very different kind of problem for mission planning than a cognitive or decision-making impairment that could emerge mid-mission. During exactly the kind of high-stakes emergency scenario a deep space crew might have to handle without the option of a quick return home. Layered on top of the cognitive research sits a smaller, more contested but still noteworthy body of evidence concerning cardiovascular health specifically. A study led by Delp and colleagues, published in Scientific Reports in 2016, reported that Apollo astronauts who traveled beyond Earth's magnetosphere to the moon showed a markedly higher rate of cardiovascular disease mortality compared both to astronauts who flew only in low Earth orbit and to a non-astronaut control group. It's genuinely important to flag the limitations of this particular study clearly and directly, because it has been the subject of real, ongoing scientific debate. It involved a very small sample, just 7 surviving Apollo lunar astronauts at the time of the analysis, and small sample epidemiological findings of this kind are inherently vulnerable to statistical noise and confounding factors that a larger dataset would be needed to properly rule out. Subsequent commentary and follow-up analysis in the literature have raised legitimate questions about the study's statistical power and its causal interpretation. What can be said fairly is that the finding, however preliminary, was concerning enough to meaningfully influence how radiation biologists think about long-duration cardiovascular risk and has helped motivate further, more rigorous research into the question. Not that it should be treated as a settled, high-confidence conclusion on its own. A separate and somewhat better established concern involves vision changes documented in astronauts following extended stays aboard the ISS, a condition now formally recognized and referred to as spaceflight-associated neuro-ocular syndrome, or SANS. And this condition, shifts in bodily fluid distribution during extended microgravity exposure, appear to alter pressure around the eye and optic nerve in some cases, producing measurable swelling of the optic disc and documented, sometimes lasting, changes to visual acuity. Some affected astronauts have shown improvement after returning to Earth. Others have not fully returned to their pre-flight baseline. SANS appears to be driven primarily by the effects of microgravity on fluid distribution rather than by radiation exposure specifically, but it belongs in this broader picture as one more example of a health effect from extended spaceflight that wasn't fully anticipated before it began showing up, empirically, in real astronauts. Taken together, this body of research, the twin studies' mixed and partly persistent findings, the rodent cognitive data from Brookhaven, the small but genuinely concerning Apollo cardiovascular signal, and the well-documented reality of SANS, doesn't add up to a case that human deep space travel is impossible, or that the people currently working on these problems are failing to take them seriously. It adds up to a case that the human body has a set of real, still only partially mapped biological limits when it comes to extended time outside Earth's protective shielding, and that pretending those limits have already been fully engineered around, when the research base clearly indicates otherwise, is not yet an accurate description of where the science ally stands. The shielding problem nobody has solved yet. Given everything laid out so far, the obvious next question is, why not just build better shielding? The honest answer is that effective shielding against galactic cosmic rays turns out to be a genuinely difficult physics problem, considerably harder than intuition suggests, and one that current engineering has not yet fully solved. The core difficulty is something radiation physicists call the spallation problem. When a high-energy galactic cosmic ray particle, moving at a meaningful fraction of the speed of light, strikes a layer of relatively thin, dense shield, energy material like ordinary aluminum, the standard structural material used in spacecraft hulls, the collision doesn't simply stop the incoming particle the way a bulletproof vest stops a bullet. Instead, it can shatter the target atom's nuclei, producing a shower of secondary particles, including energetic neutrons and other fragments, that can, in some configurations, actually deliver more biological damage to anything positioned behind the shielding than the original, unimpeded cosmic ray would have delivered on its own. This counterintuitive result is precisely why simply wrapping a spacecraft in extra aluminum plating, the intuitive first solution most people reach for, doesn't reliably solve the problem, and in some scenarios can make it measurably worse. What actually works considerably better, according to the accumulated radiation physics research on this question, is mass made from hydrogen-rich material, water, or hydrogen-dense plastics like polyethylene, which are more effective, gram for gram, at absorbing incoming particle energy without producing dangerous secondary particle showers because of specific nuclear physics properties of hydrogen's simple single-proton nucleus. The rough working figures commonly cited in the radiation shielding literature suggest something on the order of 20 to 30 grams per square centimeter of water. Equivalent shielding mass would be needed to meaningfully reduce galactic cosmic ray exposure over the course of a long-duration mission to a substantially safer level. Translated into real spacecraft engineering terms, that requirement implies a shell of water or polyethylene weighing many tens to hundreds of tons wrapped at around every habitable module a crew would actually occupy, a mass requirement that current and near-term proposed launch and propulsion systems across essentially every serious Mars mission architecture publicly discussed to date do not straightforwardly accommodate without a substantial redesign of the overall mission's mass budget, timeline, and cost. More exotic shielding concepts do exist in the research literature and are under active, genuine investigation. Active magnetic shielding systems designed to generate an artificial magnetic field around a spacecraft that would deflect incoming charged particles the way Earth's own magnetosphere does. Plasma-based shielding approaches and various superconducting deflector concepts studied at institutions including CERN and by aerospace research groups in Europe and elsewhere. These approaches remain, as of this documentary, at the laboratory demonstration and proof of concept stage, rather than flight-ready hardware and meaningful engineering. Funding and testing work remains before any of them could realistically be incorporated into an actual crewed Mars mission architecture on the kind of timeline currently being said publicly. And every additional kilogram of shielding mass a mission does carry, whatever form it takes, is necessarily a kilogram not available for food, fuel, scientific equipment, or return trip capacity. Meaning the shielding question isn't simply a matter of, can it theoretically be built? But what does building it cost the rest of the mission? A trade-off every serious mission architecture has to reckon with directly rather than assume away. None of this represents a problem some clever engineer is likely to casually resolve on a short timeline. It represents a genuine, currently unsolved constraint sitting at the intersection of nuclear physics, materials science, and spacecraft mass budgeting, one that mission planning documents and the technical literature treat with considerably more caution and specificity than the confident public timelines regularly announced for crewed Mars missions tend to convey. And the gap between the press release and the risk register. Given the genuine, well-documented severity of the radiation and shielding challenges described across the last several sections, it's fair to ask why public discussion of crewed Mars missions, from space agencies, from private companies, and from the media covering both, so rarely reflects the full weight of that difficulty. The most useful way to think about this gap is not as a matter of anyone lying, but as a predictable, well-recognized pattern in how large, expensive, politically visible engineering programs communicate about themselves. Internal risk assessment documents. NASA's Human Research Program maintains detailed, publicly available risk registers specifically cataloging known and suspected hazards of long-duration spaceflight, including radiation exposure, and researchers at institutions like NASA's Johnson Space Center and Langley Research Center regularly publish peer-reviewed papers directly addressing the scale of these unresolved challenges, tend to use considerably more cautious, DG'd, and technically precise language than the public-facing statements delivered at press conferences, in agency mission announcements, or in commercial space company marketing materials. This isn't unique to spaceflight. It's a broadly recognized pattern across large public and private engineering programs generally, where confident, forward-looking language tends to be professionally rewarded by funding bodies, by media coverage, by public and investor enthusiasm, while more cautious, uncertainty-led framing tends to generate less attention and, in some institutional contexts, less funding momentum. None of that requires any individual to be acting in bad faith. It's closer to a structural incentive built into how these programs are funded, staffed, and covered, one that consistently nudges public communication toward optimism relative to the more hedged language found in the underlying technical and risk assessment literature. The practical result is a recognizable pattern in how ambitious deep space timelines tend to unfold in public view. Confident target dates are announced. Those dates subsequently slip, sometimes repeatedly, and the individual slips tend to be described in incremental, technical-sounding terms. Schedule adjustments, supply chain issues, budget realignments, without always being clearly connected in public communication back to the underlying, harder physical and biological constraint. It's already well documented in the risk assessment literature. NASA's Artemis program offers a useful, concrete illustration of this general pattern. The initial public target for returning astronauts to the lunar surface was 2024. That date has since slipped multiple times, moving through several subsequent years as the program has encountered a mix of technical, budgetary, and schedule challenges. It's worth being clear that the Moon presents a meaningfully less severe version of the radiation and life support challenges described throughout this documentary than Mars does. Our missions are measured in days, not months, keeping total radiation exposure and other deep space health risks considerably lower. And yet even that comparatively less demanding target has proven difficult to hold to its original public timeline. That pattern is worth bearing in mind as a data point rather than a definitive prediction when evaluating how confidently to read the currently discussed mid-2030s target dates for a crewed Mars mission, given that Mars presents a substantially harder version of nearly every challenge the lunar program has already encountered. To be genuinely fair to the engineers, scientists, and agencies involved in this work, none of the above should be read as an argument that Mars exploration is being pursued dishonestly or that meaningful progress isn't being made. The specific challenges detailed across this documentary, cosmic ray shielding, cognitive and cardiovascular risk, the mass budget constraints on protected material, are precisely the kinds of problems the field's own published, peer-reviewed literature identifies as its central open questions, actively being researched by extremely capable people at NASA, ESA, and numerous universities and private companies around the world. The gap being described here isn't between honest scientists and a dishonest public narrative. It's between the necessarily hedged, technically precise language appropriate to a risk assessment document and the necessarily simplified, forward-looking language that tends to dominate public communication about ambitious, high-profile engineering programs generally. Recognizing that gap doesn't require distrust of the people doing the work. It just requires reading the risk registers as carefully as we read the press releases. A Q later, son. There's one more layer to this story that connects the Voyager 2 measurement directly back to the human spaceflight risk set across the preceding sections, and it's worth laying out carefully, including its genuine uncertainties. As established earlier in this documentary, the strength of the heliosphere's protective shielding rises and falls with the roughly 11-year solar activity cycle, strengthening during periods of higher solar activity and weakening during quieter periods. Solar Cycle 24, spanning roughly 2008 to 2019, ranked among the weakest cycles recorded in more than a century of systematic observation, and the associated solar minima produced some of the highest galactic cosmic ray flux levels measured at Earth since dedicated monitoring began in the mid-20th century. This has led some solar physicists to raise, as a genuine research question rather than a settled conclusion, the possibility that the Sun may be entering an extended period of generally reduced activity, something researchers sometimes describe, with real caution about the comparison, as loosely analogous to the well-documented Maunder minimum of the mid to late 17th century, a multi-decade stretch during which sunspots became extraordinarily rare and which coincided, for reasons still not fully or uncontroversially established, with an unusually cold period in European and North American climate history, sometimes called the Little Ice Age. It's important to represent the current state of this specific question honestly, because the scientific community is genuinely divided on it, and overstating the consensus in either direction would misrepresent where the field actually stands. Not every solar physicist working on long-term solar activity forecasting agrees that an extended quiet period, or grand minimum, is currently underway or imminent. Published forecasting models for the upcoming solar cycle 26 differ meaningfully from one research group to another, with some pointing toward a rebound in activity and others suggesting continued relative weakness. Solar cycle 25, currently in progress, has in fact come in somewhat stronger than initial official forecasts predicted, which complicates any simple narrative of a straightforward, ongoing decline. What can be stated with considerably more confidence is the narrower, already measured fact. Recent solar minima have coincided with record or near-record galactic cosmic ray flux at Earth within the space age, and even the more conservative, less alarmist interpretations of the available data still describe a heliosphere operating, on average, under somewhat lower pressure than the 20th century norm, alongside a cosmic ray environment measurably harsher than the one Apollo-era astronauts experienced. The reason this matters for the rest of this documentary's argument is that the uncertainty here cuts in a particular, important direction. The concerning implications for deep space human exposure don't require the most extreme version of the prolonged solar quiet hypothesis to hold. Even the comparatively moderate, better established version of the trend, a heliosphere and cosmic ray environment measurably less favorable than the mid-20th century baseline most existing radiation risk models and career exposure limits were originally built around, already represents a meaningful, real shift worth incorporating explicitly in mission planning, spacecraft shielding requirements, and astronaut health monitoring going forward, independent of how the more speculative long-term solar forecasting debate eventually resolves. What this means beyond Mars. Although this documentary has focused heavily on the specific challenge of crude Mars exploration, it's worth being clear that the underlying trend, a measurably thinner heliospheric shield and elevated galactic cosmic ray flux, carries implications considerably closer to home as well, affecting systems and populations that never leave Earth's immediate vicinity at all. Higher energy cosmic ray flux reaching the inner solar system translates directly into an elevated rate of what engineers call single-event upsets in electronics. Instances where a high-energy particle strikes a sensitive microelectronic component and flips a stored bit of data, potentially causing anything from a minor, self-correcting glitch to a more serious computing error, depending on the system involved and what safeguards it has in place. This is a well-established, actively managed concern for satellite operators who routinely factor radiation hardening requirements into spacecraft electronics design, specifically to guard against exactly this kind of disruption, and a rising baseline cosmic ray environment represents a real incremental increase in the design margin such hardening needs to account for going forward, particularly for the large and rapidly growing constellations of satellites now operating in low Earth orbit. Commercial aviation faces a related, more directly human-facing version of the same underlying issue. Cosmic ray exposure increases meaningfully with altitude and, independently, with proximity to Earth's magnetic poles, which is why flight crews flying frequent long-haul polar routes, connecting, for instance, North America to Asia via routes passing close to the Arctic, accumulate measurably higher occupational radiation doses over a career than crews flying primarily lower latitude routes, a well-documented occupational health consideration that airlines and aviation regulators in several countries have been monitoring and factoring into crew scheduling and exposure limits for years. A rising baseline cosmic ray environment at Earth, driven by the weakening heliospheric shielding discussed throughout this documentary, represents a modest but real upward pressure on that already monitored occupational exposure category, worth continued careful tracking rather than alarm. More broadly, an enormous and rapidly growing share of modern infrastructure, financial systems, power grid controls, autonomous vehicle systems, and the general, ever-expanding footprint of embedded, safety-critical electronics across daily life has been engineered historically against a background cost micro-ray and space weather environment implicitly treated as a roughly stable constant. The measurements described across this documentary suggest that background environment is not, in fact, a fixed constant, but a variable one, shifting over multi-decade timescales in ways tied directly to the sun's own long-term behavior. That doesn't imply any kind of imminent crisis for terrestrial electronics. The relevant changes are gradual, well within the kind of design margins already built into properly radiation-hardened systems, but it does mean that treating the heliosphere's protective effect as a fixed, unchanging background assumption rather than a genuinely dynamic system worth continued monitoring would be a quiet, easily overlooked planning error with a slowly compounding cost. T. Grand Tour. That never shall have worked. To understand why Voyager 2's 2018 measurement carries the weight it does, it helps to understand exactly how improbable the spacecraft's entire existence actually is, because almost nothing about its current, decades-overdue success was guaranteed at the outset. Voyager 2 launched on August 20th, 1977, roughly 2 weeks before its twin, Voyager 1, even though the numbering suggests otherwise, a quirk of the two spacecraft's differing trajectories rather than their launch order. Both were built to take advantage of a rare planetary alignment, occurring only once every 175 years or so, that allowed a single spacecraft to use the gravity of one outer planet to slingshot toward the next in sequence, dramatically reducing the fuel and time that would otherwise be required to visit multiple outer planets individually. This became known, informally within NASA, as the Grand Tour, and Voyager 2 remains, to this day, the only spacecraft ever to have flown past all four of the solar system's giant planets: Jupiter, Saturn, Uranus, and Neptune, a feat of trajectory planning and engineering endurance that no other mission, in the nearly 5 decades since, has attempted to repeat. The spacecraft's original primary mission was designed to last roughly 4 years, covering the flybys of Jupiter and Saturn alone. The extended tour to Uranus and Neptune was, at the time of launch, an optimistic best-case scenario rather than a guaranteed outcome, contingent on the spacecraft's electronics and power source surviving years, longer than their original design specifications strictly promised. They did. Voyager 2 reached Neptune in August 1989, 12 years after launch, delivering the only close-up images and direct measurements of that planet's atmosphere, rings, and largest moon, Triton, that humanity possesses to this day. Data that remains, decades later, the primary observational foundation for essentially everything we currently know about the outermost giant planet in our solar system. Both spacecraft carry, bolted to their exteriors, a gold-plated copper phonograph record, popularly known as the Golden Record, containing a carefully curated selection of sounds and images intended to represent the diversity of life and culture on Earth, along with spoken greetings recorded in 55 different human languages. A message assembled under the direction of astronomer Carl Sagan and a small committee of collaborators, intended less as a realistic attempt at contact with another civilization, given the near astronomical unlikelihood of the record ever actually being found and played, and more as a kind of cultural time capsule, a deliberate act of hope launched outward regardless of whether anyone would ever receive it. What makes the spacecraft's continued operation genuinely remarkable, nearly half a century on, is the sheer accumulation of engineering margin that had to hold up, largely undegraded, across a length of time its original designers had no strong reason to expect. The onboard computer systems, built with mid-1970s technology, carry a small fraction of the processing capability of an ordinary modern digital wristwatch. The radioisotope thermoelectric generators powering both spacecraft rely on the steady, entirely predictable radioactive decay of plutonium-238, power source chosen specifically because it required no moving parts and no exposure to sunlight to keep functioning. A critical design decision, given that sunlight intensity at Neptune's distance from the Sun is roughly 1,000 times weaker than at Earth, far too faint for conventional solar panels to have powered the mission. That same predictable decay, however, means the spacecraft's available power has been declining steadily and irreversibly since the moment of launch. A slow-motion countdown mission planners have been managing carefully for decades, deliberately powering down individual, non-essential instruments one at a time to stretch the spacecraft's remaining dwindling power budget as far into the future as the physics will allow. The shape of the bubble Voyager 2's direct measurement of the heliopause in 2018 didn't emerge in a vacuum, so to speak. It built directly on an earlier, complementary body of research that had already begun revealing the heliosphere to be a considerably stranger, less symmetrical structure than earlier, simpler models had assumed. For much of the 20th century, the heliosphere was generally pictured, for modeling purposes, as something close to a simple, roughly spherical or gently teardrop-shaped bubble, an intuitive, tidy approximation that made the underlying physics considerably easier to calculate, even though researchers understood it was almost certainly an oversimplification. That picture began to change substantially with the launch, in 2008, of NASA's Interstellar Boundary Explorer, or IBEX, a considerably smaller and less famous mission than the Voyager probes, but one that took a fundamentally different, complementary approach to studying the heliosphere's outer structure. Rather than flying a single spacecraft physically through the boundary at one specific point, as the Voyagers eventually would, IBEX remained in orbit around Earth and used a specialized instrument to detect and map particles called energetic neutral atoms, created when the solar wind collides with the surrounding interstellar medium at the heliosphere's edge, effectively allowing researchers to construct an indirect, whole-sky image of the heliosphere's outer boundary from a single vantage point near Earth, rather than relying on the extraordinarily slow, single-point measurements possible from a physically traveling probe. What IBEX found, beginning with its earliest data releases around 2009, surprised much of the solar physics community. A previously undetected, unexpectedly bright band of energetic neutral atom emission stretching across a significant portion of the sky, quickly nicknamed the ribbon by the researchers who found it, whose physical origin and precise shape were not well predicted by pre-existing heliosphere models, and which took years of subsequent research and refined modeling to begin explaining satisfactorily. The ribbon's discovery helped confirm what a smaller number of theorists had already begun to suspect. The heliosphere's outer boundary is not a smooth, simple, predictable shape, but something considerably more structured, dynamic, and locally variable than the earlier textbook picture had assumed. Findings that Voyager 1 and Voyager 2's subsequent direct, in situ crossings in 2012 and 2018 respectively. Both helped to further refine and, in several specific respects, complicated rather than simply confirmed. It's also worth noting that our own heliosphere is very unlikely to be a unique structure in the wider galaxy. Astronomers use the term astrosphere to describe the equivalent structure surrounding other stars, and while direct observation of another star's astrosphere remains extraordinarily difficult given the vast distances involved, indirect evidence, particularly from studies of how the light of more distant background stars is subtly absorbed, or altered as it passes near a nearer star's presumed astrospheric boundary, suggests these structures are a common, expected feature of stellar systems generally, varying considerably in size and shape depending on a given star's particular combination of stellar wind strength, motion relative to the surrounding interstellar medium, and the density of gas in whatever specific region of the galaxy that star happens to be passing through. Our own heliosphere's asymmetric, ribbon-marked, dynamically shifting structure, in other words, likely represents something closer to the ordinary condition for a star like our Sun, rather than any kind of unusual anomaly specific to our own solar system, a reminder that the protective bubble surrounding Earth, however important it is to us specifically, is very probably just one unremarkable example of a structure that likely surrounds a significant fraction of the galaxy's other sun-like stars as well. Mars on paper versus Mars in practice. The gap between confident public timelines and the harder underlying physics described throughout this documentary is not a new phenomenon specific to the current era of Mars planning. It has a genuinely long history worth understanding in its own right, because that history helps explain why the pattern keeps recurring. Serious technical planning for a crewed Mars mission dates back further than most casual observers realize. Wernher von Braun, the German-American rocket engineer, who would later lead development of the Saturn V rocket that carried Apollo astronauts to the moon, published a detailed technical mission architecture for a crewed Mars expedition as early as 1952, envisioning a large fleet of vehicles and a substantial crew based on the propulsion technology available or anticipated at the time. Von Braun's plan, like most of the Mars mission concepts that would follow it across the subsequent 7 decades, including NASA's own space exploration initiative studies in the late 1980s and early 1990s, various Mars design reference mission architectures developed and revised repeatedly from the 1990s through the 2010s, and the current mix of NASA and commercial architecture proposals, actively discussed today, has consistently run into the same fundamental, recurring cluster of unresolved challenges. Propulsion systems capable of reasonably short transit times, life support systems reliable enough to operate unsupported for years at a stretch, and, threading through nearly every serious technical study across this entire 70-year span, the radiation shielding problem detailed earlier in this documentary, which has never yet been fully, practically solved within the mass and cost constraints any real mission would actually have to work within. What has changed meaningfully across that 70-year span is less the underlying physics, which has remained essentially constant, and more the institutional and commercial landscape surrounding Mars mission planning. The current era features a more complex, multi-actor landscape than earlier decades. NASA's own Artemis program, explicitly framed as a stepping stone toward eventual Mars missions via renewed lunar exploration and infrastructure development. A range of privately funded efforts, most prominently SpaceX's Starship program, explicitly marketed around aggressive, publicly stated Mars timelines considerably more optimistic than most government agency project IONs, and a broader ecosystem of academic, governmental, and commercial actors, each operating under somewhat different incentive structures, funding cycles, and public communication norms. This more crowded, competitive landscape has, if anything, tended to intensify rather than moderate the general pattern of ambitious public timeline announcements outrunning A more cautious pace suggested by the underlying technical risk assessment literature, given that commercial space marketing in particular operates under investor and public attention incentives that reward bold, headline-friendly target dates in a way government-only programs of earlier decades did not experience to nearly the same degree. None of this history is meant to suggest that meaningful technical progress hasn't occurred. Propulsion technology, life support systems, autonomous systems, and material science have all genuinely advanced considerably since von Braun's 1952 proposal, and current mission concepts are, in most respects, built on a dramatically more capable technological foundation than anything available in earlier decades. But the specific, persistent recurrence of the radiation shielding problem across 7 full decades of otherwise rapidly advancing Mars mission planning is itself a meaningful data point, worth weighing seriously against any specific near-term timeline currently being discussed publicly. A challenge that has remained essentially unresolved across 70 years of otherwise remarkable technological progress is not, on the available evidence, a challenge likely to be fully solved within the next decade simply because a confident public announcement says it will be. Mind-in-the-box radiation exposure, extensively documented across the middle sections of this film, is far from the only significant human health challenge a multi-year Mars mission would present. And it's worth spending some time on a second, less physically dramatic but equally well-documented category of risk. The psychological toll of extended isolation and confinement, a challenge researchers have studied directly through a series of dedicated ground-based simulation experiments over the past several decades. The most extensive of these studies, a Russian-led international project called Mars 500, confined a crew of 6 volunteers inside a sealed, windowless facility in Moscow for 520 days beginning in 2010, a duration deliberately chosen to match the approximate length of a full round-trip crewed Mars mission, including transit time in both directions and a period on the simulated Martian surface, with no physical contact with the outside world beyond communications deliberately delayed, to simulate the real Mars-Earth signal lag, which stretches, depending on the 2 planets' relative positions, from several minutes up to roughly 22 minutes each way. The results, published across a range of peer-reviewed psychological and physiological journals in the years following the experiment's conclusion, documented measurable disruptions to crew members' sleep patterns, mood stability, and cognitive performance over the course of the confinement, along with the emergence, in at least some crew members, of symptoms consistent with a recognized condition researchers term sensory monotony, a form of psychological fatigue arising specifically from prolonged exposure to an unchanging, confined physical and social environment, distinct from ordinary boredom in its documented physiological correlates. A separate, complementary series of shorter duration studies conducted by the University of Hawaii's HICS program at a remote, Mars analog habitat on the slopes of Mauna Loa between 2013 and 2018 similarly documented measurable interpersonal tension, communication breakdowns, and mood disturbances accumulating among small, isolated crews over missions ranging from 4 months to a full year, even under conditions considerably less physically demanding than an actual Mars mission would present, given that HICS crew members retained the ability to leave the habitat in an emergency, something a genuine deep space crew would not have. Researchers involved in both programs have generally converged on a broadly similar conclusion. Crew selection, team composition, and psychological support systems represent a distinct, separately significant risk category for any future Mars mission, requiring dedicated research and mitigation planning that runs in parallel to, rather than in place of, the physical radiation and life support challenges detailed earlier in this documentary. It's worth being clear that psychological risk research of this kind, however carefully conducted, faces its own significant limitations when it comes to predicting outcomes for an actual Mars mission. Ground-based analog studies, however rigorously designed, cannot fully replicate the psychological weight of genuine, irreversible physical distance from Earth. The real rather than simulated risk of mission-ending catastrophic failure, or the specific combination of radiation exposure and confinement stress a real crew would experience simultaneously rather than in isolation from one another, as most analog studies to date have effectively tested them. This remains, like several other categories of risk described throughout this documentary, a genuinely active area of ongoing research rather than a fully solved problem. One more reason the confident public timelines surrounding near-term crewed Mars missions deserve to be weighed against the more cautious, hedged pace suggested by the underlying research literature across multiple, largely independent risk categories, physical and psychological alike. What Apollo risked, and what we're asking now. It's worth directly addressing an objection that surfaces naturally at this point in the argument. Didn't the Apollo program already prove that human beings are willing and able to accept serious risk in pursuit of ambitious space exploration goals? The honest answer is yes, but the specific category and structure of the risk Apollo astronauts accepted was meaningfully different from what a Mars mission would ask of its crew, in ways worth being precise about rather than glossing over. Apollo-era risk was concentrated overwhelmingly in acute, mission-critical failure events: a launch vehicle malfunction, a life support system failure, a lunar landing or ascent engine problem, the kinds of catastrophic, immediate failures that claimed the lives of the Apollo 1 crew during a 1967 launch pad test and came close to claiming the Apollo 13 crew in 1970. These were genuinely severe risks, openly acknowledged at the time by both the astronauts themselves and NASA's own internal engineering assessments. The astronauts who accepted them deserve full credit for that willingness. But the radiation exposure and cumulative physiological risk profile documented across this film represents a categorically different kind of hazard. Not a single, acute, survive or don't event, but a slow, cumulative, statistically distributed risk to long-term health, elevated cancer probability, documented cognitive effects, contested but concerning cardiovascular signals, and the largely unprecedented cumulative burden of 18 to 30 months of continuous exposure outside planetary magnetic protection. A risk structure closer to a long industrial occupational hazard than to the dramatic, immediate failure scenarios most closely associated with the Apollo program in popular memory. This distinction matters for how honestly a Mars mission's risk can be communicated to its eventual crew, and to the public funding and supporting it. Apollo astronauts could be told, with reasonable clarity, the acute probability of catastrophic mission failure based on the engineering data available at the time, and could make an informed decision to accept that specific, bounded risk. A Mars crew, by contrast, would be accepting a risk profile that current research, as this documentary has tried to lay out honestly, cannot yet fully quantify with the same degree of confidence. Genuine uncertainty remains around the precise magnitude of cognitive risk suggested by rodent studies around how directly the small, contested Apollo cardiovascular signal should be weighted, and around how effectively any given shielding architecture would actually perform against the specific radiation environment a real mission would encounter. Informed consent, in other words, is measurably harder to achieve cleanly for a Mars mission than it was for Apollo. Not because today's astronauts are any less willing to accept risk than their predecessors, but because the specific risk being asked of them is less completely characterized by the available science. A distinction that argues, if anything, for more transparency and more caution in how mission timelines and residual risk are communicated publicly, not less. None of this is an argument that the risk is therefore unacceptable, or that a Mars mission shouldn't ultimately proceed once the relevant science and engineering have matured further. Human beings have a long, genuinely admirable history of accepting serious, well-understood risk in pursuit of exploration, discovery, and achievement. And there is every reason to expect qualified astronauts will continue to be willing to do so for a Mars mission specifically, once offered a fully honest account of what's actually being asked of them. The argument this documentary has tried to make is narrower, that the account currently being offered to the public in the confident timelines and forward-leaning language typical of press conferences and marketing materials does not yet fully reflect the more hedged, uncertain, still actively researched picture found in the underlying technical and risk assessment literature. And that gap is worth closing, for the sake of both the future crew being asked to accept the risk and the public being asked to fund and support the mission around them. Reading the room. How this story got told. It's worth looking directly at how the Voyager 2 heliopause crossing was actually covered in late 2018, because the specific pattern of that coverage illustrates the broader gap this documentary has been describing more concretely than any general description of the phenomenon can. Major outlets covering the story in November and December 2018 overwhelmingly led with the milestone framing. Voyager 2 becomes the second human-made object to reach interstellar space, following in its twin's footsteps 6 years after Voyager 1's own crossing in 2012. Coverage generally included brief, accurate technical detail about the heliopause and the general concept of the heliosphere as a protective bubble, often illustrated with an artist's rendering of the vast, teardrop-shaped structure. Ed Stone's evident enthusiasm, quoted extensively across outlets, became something close to the emotional center of the story. A widely respected veteran scientist marking a genuinely moving personal and professional milestone after decades associated with the mission. All of that coverage was accurate, and none of it was misleading in any narrow, sentence-by-sentence sense. What was largely absent across the great majority of that initial wave of general audience coverage was the specific, more technical detail contained in the companion papers, subsequently published in Nature Astronomy in 2019, the sharpness of the density boundary, the elevated cosmic ray readings on the interstellar side, and the ways in which several specific measurements diverged from pre-existing model predictions. This isn't a criticism of any individual reporter or outlet. General audience science journalism operates under real space and attention constraints, and a milestone anniversary framing is, by any reasonable editorial judgment, a more accessible entry point for most readers than a detailed discussion of plasma-dense anti-gradients. But the practical effect of that near-universal framing choice was that the specific, more consequential technical findings took considerably longer to reach public awareness than the milestone framing itself did, surfacing gradually over the following months and years primarily through specialist science publications, university press releases tied to the Nature Astronomy papers publication, and, more recently, longer-form science communication specifically focused on connecting the heliopause measurements to the human spaceflight radiation risk questions this documentary has centered on. This pattern, a simplified, celebratory initial framing followed, considerably later and with much smaller reach, by more technically complete follow-up coverage, is not unique to the Voyager 2 story. It's a broadly recognizable pattern across a great deal of science journalism generally, particularly for stories originating from large, well-resourced institutional press operation with a strong, understandable interest in generating positive public attention around milestone achievements. Recognizing the pattern doesn't require assuming bad faith on the part of scientists, science communicators, or journalists involved at any stage. It simply means recognizing that the version of a scientific story most people actually encounter, especially for a story that briefly surfaces in general news coverage before receding from public attention, is very often the simplified, milestone-focused version, and that meaningfully engaging with the fuller, more technically complete picture of the kind this documentary has tried to assemble, generally Riz deliberately seeking out the specialist literature and longer-form coverage that the initial wave of general coverage rarely has the space or the incentive to fully include. The cost of being wrong in either direction. Before closing, it's worth directly addressing a fair, important objection to the entire argument this documentary has made. Isn't there a real risk of overcorrecting, of tipping from an unhelpfully optimistic public narrative into an unhelpfully pessimistic one, discouraging exactly the kind of ambitious exploration that has produced so much of humanity's most valuable scientific knowledge? The concern is legitimate, and it deserves a direct, honest answer rather than a dismissal. There is a genuine, well-recognized cost to excessive caution in exploration and scientific ambition generally, worth naming plainly. Programs that are perpetually delayed by an unwillingness to accept any residual uncertainty risk, never launching at all, and history offers real examples of valuable, ultimately successful missions that faced significant internal skepticism and nearly didn't proceed because of legitimate but ultimately manageable risk concerns raised during their planning. Excessive risk aversion carries its own opportunity cost, measured in delayed discovery, delayed engineering progress, and delayed inspiration for the next generation of scientists and engineers who might otherwise be drawn toward the field by genuinely ambitious, forward-looking goals. A documentary arguing only for caution, without acknowledging this cost honestly, would itself be offering an incomplete picture. But there is an equally real, if less frequently discussed, cost on the other side of the ledger. A mission launched, or a timeline publicly promised, before the underlying physical and biological risk picture is genuinely well enough understood, risks consequences considerably more severe than a schedule slip. It risks the health and safety of the specific human beings asked to fly the mission, based on a risk assessment that turns out, after the fact, to have been meaningfully incomplete. It risks a catastrophic mission failure that could set back public and political support for the entire field of deep space human exploration by a decade or more, in a way a series of honestly communicated schedule delays would not. And it risks a slower, more corrosive kind of damage as well. A repeated pattern of confidently promised timelines failing to materialize, gradually eroding public trust in space agencies and companies' forward-looking statements more broadly, making it harder, not easier, to sustain the kind of long-term public and political support ambitious exploration programs actually require to succeed over the multi-decade timescales they typically demand. The argument this documentary has tried to make sits specifically in between these two failure modes, rather than favoring either one. It is not an argument for abandoning Mars exploration, slowing research funding, or treating the radiation and physiological risks described throughout this film as insurmountable, permanent barriers. The pace of research into shielding technology, radiation biology, and psychological resilience has genuinely accelerated in recent years. And there is no strong reason to assume these problems are permanently unsolvable given continued investment and time. It is, instead, an argument for closing the specific, documented gap between the confidence of public timeline announcements and the more hedged, cautious language found in the underlying risk assessment and peer-reviewed literature, not because caution is inherently more virtuous than ambition, but because an accurate, honestly communicated picture of remaining technical and biological uncertainty is the foundation every subsequent good decision about funding, mission design, and crew safety actually depends on. Optimism untethered from that foundation isn't ambition. It's just a more comfortable way of not looking directly at the numbers. A double jeopardy of the destination itself. It's worth being explicit about a detail easy to overlook amid all the discussion of transit phase radiation exposure. Mars itself does not offer meaningful relief once a crew actually arrives. Unlike Earth, Mars lacks a global, internally generated magnetic field of its own. Mars's core appears to have cooled and its internal dynamo shut down early in the planet's history, likely within its first billion years, taking its planetary magnetic shielding down with it. What remains today is a patchwork of localized, comparatively weak magnetic fields frozen into certain regions of the Martian crust, remnants of that ancient, long-dormant dynamo, offering only spotty, incomplete protection rather than anything resembling Earth's continuous, planet-wide magnetospheric shield. Mars's atmosphere, the second layer of terrestrial-style protection, is similarly compromised. At roughly 1% the surface pressure of Earth's atmosphere and composed overwhelmingly of carbon dioxide rather than the denser nitrogen-oxygen mixture protect Earth's surface. The Martian atmosphere provides considerably less shielding mass between the surface and incoming cosmic radiation than Earth's atmosphere does. NASA's Curiosity rover, carrying the same radiation assessment detector instrument that measured the transit phase dose discussed earlier in this documentary, has continued recording radiation levels at the Martian surface since its 2012 landing, and the results are consistent with this picture. Surface radiation dose rates on Mars run considerably higher than anywhere on Earth's surface, including high altitude and polar regions where terrestrial cosmic ray exposure is already elevated, though still meaningfully lower than the fully unshielded dose rate experienced during transit through open space, since Mars's thin atmosphere and the bulk of the planet itself do provide at least partial, if incomplete, shielding once a crew is actually standing on the surface. The practical implication is that a Mars mission's radiation exposure problem doesn't end the moment a crew successfully lands. It simply shifts to a somewhat reduced but still significantly elevated rate, sustained continuously for however long the surface stay lasts, which in most currently proposed mission architectures runs anywhere from several weeks in an early minimal stay design to well over a year in more ambitious architectures designed to wait for the next favorable Earth-Mars transfer window before returning. Longer surface stays, in other words, reduce the number of return transit windows a mission has to wait through, but extend the total time a crew spends exposed to Mars' zone significantly higher than Earth's surface radiation environment. A genuine design trade-off between transit efficiency and surface exposure duration that ion architects have to weigh carefully, with no straightforwardly risk-free option currently available on the table. This is precisely why several proposed Mars mission architectures include specific plans for partially subterranean or otherwise heavily shielded surface habitats, potentially using several meters of packed Martian regolith, the loose surface soil and rock covering most of the planet, as a comparatively low-cost, locally-sourced radiation shield, a solution that sidesteps the mass launch cost problem plaguing in-transit shielding, discussed earlier in this documentary, since the shielding material in this case doesn't need to be carried from Earth at all, but introduces its own separate engineering challenges around excavation, habitat construction, and the practicalities of building safe, reliable subterranean living quarters on a remote planet using robotic or crew labor with no opportunity for outside resupply if something goes wrong during construction. What getting this right would actually look like. It would be incomplete, and arguably unfair to the researchers working on these problems to close this documentary without acknowledging the genuine, active progress being made on several fronts specifically aimed at closing the gaps described throughout this film. Progress worth taking seriously as a counterweight to the more cautionary tone of the preceding sections. On the shielding front, beyond the passive water and polyethylene and regolith burial approaches already discussed, mission architects have increasingly converged on the concept of a dedicated storm shelter, a small, heavily shielded compartment within a larger, more lightly shielded spacecraft, intended not to protect a crew from routine galactic cosmic ray background exposure across an entire mission, which, as discussed earlier, would require a practically large mass budget to fully address, but specifically to protect crew members during the comparatively rare but acutely dangerous event of a major solar particle event, a kind of unpredictable, intense burst of solar radiation capable of delivering a large, medically significant dose in a matter of hours. Because solar particle events, unlike the constant galactic cosmic ray background, arrive with at least some advance warning, typically on the order of tens of minutes to several hours depending on the specific event. A storm shelter approach allows a mission to carry a much smaller total mass of heavy shielding material, positioned strategically around a single small compartment rather than an entire spacecraft, while still providing meaningful protection during exactly the highest acute risk windows of a mission. On the pharmacological and biomedical front, researchers are actively investigating a range of potential radioprotective and radiomitigative compounds, substances that might reduce cellular damage from radiation exposure, either when taken preventively before exposure or administered afterward to help mitigate ongoing damage. Building on decades of related research originally motivated by terrestrial concerns like nuclear medicine and radiation oncology, this research remains at a comparatively early stage, specifically as applied to the particular radiation profile of galactic cosmic rays, which differs meaningfully from the more thoroughly studied X-ray and gamma-ray exposure profiles most existing radioprotective research has historically focused on, but it represents a genuinely active and reasonably well-funded area of ongoing investigation rather than a neglected one. On the propulsion front, a different but complementary strategy focuses not on better shielding, but on simply reducing the total time a crew spends exposed to the deep space radiation environment in the first place, by developing propulsion systems capable of meaningfully faster transit times than the conventional chemical rockets underlying most current mission architecture proposals. Nuclear thermal and nuclear electric propulsion concepts, both actively being researched and, in some cases, ground-tested by NASA and partner organizations as of this documentary's writing, offer the theoretical potential to reduce Mars transit time meaningfully compared to conventional chemical propulsion, which would proportionally reduce total accumulated radiation dose even without any improvement in shielding technology at all. These systems remain in active development rather than flight-ready status, and meaningful engineering and safety testing work remains before any could be incorporated into an actual crewed mission. But the underlying physics argument that reducing exposure time is at least as valuable a lever as improving shielding mass, and considerably more mass efficient in some respects, has gained real traction within the mission architecture research community in recent years. Taken together, these three complementary lines of active research, targeted storm shelter shielding rather than whole spacecraft shielding, pharmacological risk mitigation, and faster propulsion to reduce total exposure time, represent a genuinely serious, multi-pronged research effort specifically aimed at closing the gap this documentary has spent considerable time describing. None of them, individually or combined, currently constitutes a fully solved, flight-proven answer to the radiation challenge as of this documentary's writ. But their existence, and the genuine institutional investment behind them, is worth weighing honestly alongside the more cautionary material presented earlier. This is a problem under active, well-resourced attack, even if it isn't yet a problem that's been fully solved. A note on the numbers. Before returning to Voyager 2 for this documentary's final section, it's worth pausing briefly to be transparent about the nature of the figures cited throughout this film, because intellectual honesty about uncertainty has been one of this documentary's central arguments, and that standard should apply to this film's own claims just as much as to the press releases and mission timelines it has scrutinized. Several of the specific numbers cited across this documentary, the Curiosity Rad transit dose figures, the NASA career radiation exposure limits, the water equivalent shielding mass estimates, the cosmic ray flux increase during recent solar minima, represent genuine, published figures drawn from the peer-reviewed and agency technical literature, but in most cases they also carry real ranges of uncertainty, methodological caveats, or ongoing scientific refinement that a documentary of this length and format cannot fully capture in every instance without becoming unwatchably dense. Where this documentary has cited a specific figure or range, that figure should be understood as a reasonable, literature-grounded approximation useful for conveying the general scale and severity of a given risk, rather than a precise, final, universally agreed-upon number immune to future revision as research continues. Similarly, where this documentary has flagged a specific finding as contested or preliminary, the small sample Apollo cardiovascular study, the rodent cognitive research, the open debate over an extended solar minimum, that flagging reflects a genuine, honest attempt to represent the actual state of scientific consensus or disagreement on that specific point, rather than an attempt to either dismiss or overstate the underlying concern. Science reporting done responsibly requires holding two things simultaneously: taking preliminary, contested findings seriously enough to discuss them honestly, while also being clear about exactly how preliminary or contested they currently are, so that a viewer walks away with an accurate sense of confidence levels rather than a flattened picture in which every claim carries equal certainty. This documentary has tried, throughout, to model the kind of communication it has spent considerable time arguing is too often missing from public discussion of these issues: specific, sourced, appropriately hedged, and honest about the boundary between what's well established and what remains genuinely open. Whether it has succeeded at that standard as consistently as it should have is, fairly, for you to judge. But the attempt itself is the whole point. The argument this documentary has made only holds together if it's willing to apply the same standard of careful, honest uncertainty to itself that it has asked of space agencies, mission planners, and the media covering them. How other high-stakes fields learned to talk about risk. It's worth closing this documentary's argument with a comparison to two other fields that have already, over painful decades, worked through versions of exactly the communication gap described throughout this film, not because spaceflight should simply copy their solutions wholesale, but because their experience offers a genuinely useful, evidence-based template for what closing that gap can actually look like in practice. Commercial aviation offers perhaps the clearest example of an industry that transformed its relationship with risk communication over the second half of the 20th century. Early commercial aviation, in the decades following World War II, was characterized by a pattern not unlike the one described throughout this documentary: confident public messaging about safety and reliability, sitting alongside a technical accident investigation culture that, in its early years, often struggled to translate hard-won safety lessons into public communication or even into consistent industry-wide practice. What changed gradually across subsequent decades was the development of a rigorous, standardized, and, crucially, largely blame-neutral accident investigation and reporting culture, exemplified by bodies like the National Transportation Safety Board in the United States and its international counterparts, built specifically around the principle that honestly, thoroughly documenting what actually went wrong, without either minimizing it publicly or treating the disclosure itself as an admission of institutional failure, was the single most effective way to prevent future accidents. The result, measured over decades, has been one of the most dramatic safety improvements achieved by any major transportation industry in modern history. A trajectory made possible specifically because the field developed a professional culture and supporting institutions that rewarded honest risk disclosure rather than punishing it. The nuclear power industry offers a related, if more painful, version of the same underlying lesson. Following the 3 Mile Island accident in 1979, and, considerably more severely, the Chernobyl disaster in 1986, the international nuclear industry underwent a substantial, forced reckoning with the gap between confident public safety messaging and the more complex, hazard-laden technical reality underlying a nuclear plant operation. The reforms that followed, including the establishment of bodies like the World Association of Nuclear Operators, dedicated specifically to facilitating detailed safety information sharing across national and corporate boundaries that commercial competition would otherwise discourage, were built on the hard-earned recognition that an industry's long-term public trust and operational safety both depend on a culture of transparent, technically detailed risk communication, even when that communication is less immediately reassuring than a simplified public message would be. It's worth being honest that this transformation in the nuclear industry came only after two major accidents forced the issue. Rather than being adopted proactively, a sobering data point in itself, suggesting that voluntary transparency reform, absent some forcing event, is historically difficult to achieve even when the underlying case for it is well understood in advance. The comparison to human spaceflight is not perfect. Aviation and nuclear power are both far more mature industries, operating at vastly larger scale with correspondingly larger and more established safety bureaucracies than the comparatively young, still rapidly evolving field of crewed deep space exploration. But the underlying pattern both fields eventually learned, sometimes only after real tragedy forced the lesson, is directly relevant to the argument this documentary has tried to make. A field's long-term success and public trust are best served by a communication culture that treats honest, technically detailed risk disclosure as a strength rather than a liability, well before any specific mission failure forces that lesson to be learned the hard way. Human spaceflight has its own sobering historical examples of exactly this dynamic. The Space Shuttle Challenger disaster in 1986 involved, according to the subsequent Rogers Commission investigation, known internal engineering concerns about O-ring performance in cold weather that had not been adequately weighted against schedule, and public communication pressure in the final launch decision. The Columbia disaster in 2003 involved a broadly similar pattern, in which engineering concerns about foam debris strikes were, according to the subsequent Columbia Accident Investigation Board report, insufficiently escalated within an organizational culture that had, over time, come to normalize a known risk rather than continuing to treat it with appropriate urgency. Both investigations, notably, identified organizational communication culture, not merely a single hardware failure, as a central contributing factor. Held against that specific history, the argument this documentary has tried to make throughout carries an additional, sharper edge. The gap between confident public Mars timelines and the more cautious, hedged language of the underlying risk assessment literature is not merely an abstract concern about accurate science communication for its own sake. It's the same structural pattern: optimistic public messaging outrunning known, documented technical risk, that has, in this field's own specific history, previously preceded exactly the kind of catastrophic failure a more honest, transparent risk culture might have helped prevent. Learning that lesson proactively, rather than waiting for it to be forced by tragedy the way it was for aviation, nuclear power, and human spaceflight's own past, is precisely the kind of correction this documentary has tried to argue for. The message from the edgy. Which brings this story back to where it began. A small, aging spacecraft, 6 billion miles from home, whose 2018 measurement carries considerably more weight than the celebratory headlines at the time conveyed. It's worth taking a moment to sit with the genuine strangeness of Voyager 2's continued existence. It was designed for a primary mission lasting roughly 4 years, intended to fly past Jupiter and Saturn, and, in its extended mission, Uranus and Neptune as well. It has now been operating for nearly half a century, quietly outliving the specific political and technological era that built it, along with a great many of the assumptions embedded in its original design. It is currently so distant that a radio signal traveling at the speed of light takes well over 19 hours to reach it, one way. Its onboard computer carries a small fraction of the processing power and memory of an ordinary modern greeting card. Its power source, a radioisotope thermoelectric generator relying on the steady, predictable decay of plutonium-238, is fading on a well-understood and unavoidable physical schedule, and mission engineers have already begun the careful sequential process of switching off individual scientific instruments, one at a time, to conserve the spacecraft's dwindling electrical power for as long as possible. Current projections suggest the spacecraft will likely lose the ability to power any remaining instruments and fall silent sometime around the mid-2030s. And in that long, slow, quietly diminishing final phase of its working life, it delivered arguably the single most consequential measurement of its entire mission. Not a photograph, not one of the dramatic planetary flyby images that made the original Voyager mission famous in the late 1970s and 1980s, but a number, a density reading, a cosmic ray count, a boundary that turned out sharper than the models predicted, wrapped around a solar system many of us had quietly, comfortably assumed we already understood reasonably well. The two Voyager spacecraft will likely continue transmitting in increasingly limited form for a few more years yet, before falling permanently silent sometime around the mid-2030s as their power sources finally drop below the threshold needed to operate even their most essential remaining systems. After that point, both will continue drifting outward, coasting silently through interstellar space for what is, for all practical purposes, an unimaginably long time to come, outlasting by an enormous margin every human structure currently standing, and very likely every person alive to read this sentence today. Each one still carrying its golden record, engraved with greetings recorded in 55 human languages, moving steadily onward through a galaxy that neither notices nor particularly cares what Voyager 2 actually confirmed when its 2018 measurement is read in full, alongside the decades of cosmic ray human physiology. And so, our activity research this documentary has tried to lay out honestly is not a reason for panic, and it isn't evidence of any deliberate cover-up. It's a genuinely important, still underappreciated data point. The shield that has made every moment of human existence, and every moment of life on Earth more broadly, possible, is real, is measurable, and is not a fixed, permanent given. It is a dynamic, physically variable structure tied to the ongoing behavior of our own sun, currently measured to be somewhat thinner and somewhat less effective than it was during earlier, better studied decades of the 20th century. And that fact deserves a meaningfully larger place in how we plan the next several decades of human spaceflight than it has generally been given in public conversation so far. Now, none of what this documentary has laid out is an argument against exploring Mars or against deep space exploration more broadly. It's not a claim that NASA, ESA, or any of the private companies working on these problems are being dishonest, or that the extraordinary engineering and scientific work already underway is somehow wasted or misguided. Quite the opposite. The specific challenges detailed here are precisely the challenges the field's own best researchers are actively, seriously working to solve, often years or decades ahead of when the public conversation catches up to the difficulty involved. What this documentary has tried to argue is narrower and, hopefully, more useful. That honest engineering has to start from honest measurement, and that the measurement Voyager 2 sent home in 2018, read in full, alongside everything we've since learned about cosmic ray trends, deep space radiation exposure, and its documented effects on the human body, deserves a more prominent place in how confidently the public is invited to think about near-term crewed Mars timelines. The gap between a risk register's careful, hedged language and a press conference's confident, forward-looking framing isn't evidence of dishonesty, but it is a gap worth noticing and worth correcting for whenever we try to form our own honest picture of what's actually still unsolved. Think back across everything this documentary has actually covered, because taken individually, each piece can seem like a narrow technical detail. A plasma density gradient, a millisievert figure, a contested 7-astronaut cardiovascular study, a rodent's slightly slower maze time in a Long Island particle accelerator facility. It's only when those pieces are set down next to each other, in the order this film has tried to lay them out, that the larger shape becomes visible. A protective structure most of humanity had never had reason to think about, now measured directly for the first time, and found to be thinner than assumed. A body evolved entirely within that structure, showing early, still incomplete, understood signs of strain the moment it's asked to operate outside it for any real length of time. A shielding engineering problem that has resisted a full solution across 7 decades of otherwise extraordinary technological progress, and a public conversation that has, understandably but consequentially, tended to compress all of that genuine complexity down into a small number of confident, forward-leaning sentences. None of the individual facts in that list is secret. Every figure and every study cited across this documentary sits in the ordinary, publicly accessible scientific record, published in peer-reviewed journals any interested person can eventually find and read. What's been missing, more than any single hidden fact, is the deliberate act of laying all of it out together, in one place, in plain language, without either exaggerating the danger into something apocalyptic or softening it back down into the tidy, milestone-shaped story most of us actually encountered back in 2018. That act of assembly, not new data, just an honest arrangement of data that already existed, is, in the end, most of what this documentary has actually tried to do. There's a particular kind of quiet responsibility that comes with living inside a shield you didn't build and rarely think about, and it's worth sitting with for a moment rather than rushing past. Every person who has ever lived, without a single exception across the entire span of human history, has done so entirely within the protection this documentary has spent its runtime describing. Every argument, every discovery, every love, every grief, every ordinary Tuesday afternoon anyone has ever lived through happened underneath the same nested structure of shielding. Heliopause, termination shock, heliosphere, magnetosphere, atmosphere, doing its quiet, continuous, entirely unglamorous work, without applause, without headlines, without ever once being asked to take a day off. We are, every one of us, the direct beneficiaries of a piece of cosmic architecture we didn't design, can't repair, and until very recently couldn't even measure with any real precision. It's worth holding, alongside everything cautionary this documentary has laid out, an honest measure of genuine wonder as well, because the two are not actually in tension with each other. The fact that a spacecraft launched in 1977, built with technology that would strike most modern engineers as almost primitive, managed to survive 4.5 decades of continuous operation, cross a boundary more than 12 billion miles from its launch pad, and still transmit back a scientifically usable signal, is itself an extraordinary testament to what careful, patient, unglamorous engineering can achieve across a long enough timescale. The same is true, in a different register, of every researcher who has spent a career carefully measuring neutron-monitored data or exposing laboratory rodents to simulated cosmic ray doses or tracking the slow, statistically noisy signal in a small cohort of aging Apollo astronauts. Unglamorous, rarely headline-making work accumulated patiently over decades, that is precisely what makes an honest picture like the one this documentary has tried to assemble possible in the first place. Caution and wonder, in the end, come from the same source. A willingness to look directly and carefully at what's actually there, rather than settling for either an falsely reassuring story or an unnecessarily frightening one. The next time you step outside at night, look up and find the familiar shapes of the stars overhead. It might be worth remembering, if only for a moment, exactly what stands between you and them. Not just the atmosphere, not just Earth's own magnetic field. The entire nested structure of shielding described across this documentary. Heliopause, termination shock, heliosphere, magnetosphere, atmosphere. Working together, continuously, largely unnoticed, to make every ordinary moment of human life possible in the first place. It's a structure none of us built, and one most of us have spent our entire lives never once having to think about. We have now, for the first time in human history, actually measured how thin part of that structure really is. What we choose to do with that measurement, how carefully we let it shape the next several decades of spaceflight planning, mission architecture, and public expectation, is a question still very much open, and one worth taking seriously, carried home to us by a small, fading 45-year-old spacecraft that was never originally built to answer it at all. It was sent out to photograph planets. It ended its working life measuring the walls of the room we've all been living in the whole time, and reporting back, faithfully, exactly what it found. If this kind of careful, honest deep dive is something you'd like to see more of, subscribing genuinely does help. It tells us these longer, more detailed explorations are worth the time they take to put together, and it's the best way to make sure you don't miss the next one.